Okay, thanks everyone for coming. Today we have a talk by Dr. Nathan Sturtevant from the University of Alberta. Nathan is a candidate for the faculty position in games here, so it's especially important that at the end of the talk, when you have questions, you wait until we can get one of the house mics over to you so we can record your question as well as Nathan's answer. So Nathan is an associate, an adjunct assistant professor in computer science at the computer science department at Alberta. He got his PhD in 2003 from UCLA under the direction of Rich Korf there. And today he will be talking about new forms of memory-based heuristics in the context of search. So thank you, Nathan.
Okay. So thank you for coming this morning. I know in our department, 10 a.m. talk generally doesn't get very good attendance, so I'm glad to see people are here. Before I start my talk, I'm going to meet with a number of people today, so I just wanted to give a little bit of overview of some of my research interests and contributions. Today I'm going to be talking about heuristic search and in particular single agent search, and so we'll talk about some of the applications to games there as well as sort of the broader topic. So I have some algorithms here for fast and efficient planning using abstraction and refinement. I'll talk a little bit about that. I'm also very interested in heuristic and search in higher dimensional search spaces, and I have some work there. My thesis was actually in the area of multi-agent search algorithms. This is an area where people thought you actually aren't able to reduce the size of the search space like you would do something with alpha beta pruning, but I actually was able to show that it is possible to do that. I've looked at, in this domain, we've looked at reinforcement learning for learning evaluation functions for players. We've looked at opponent modeling. When you go to games with more than 2 players or situations with more than 2 players, the model of the way your opponents are going to play a game is actually very important, the way you're going to interact with them. So we've looked at some algorithms to try and do that. UCT is an algorithm that's being used recently, was popularized for analyzing games, in particular where we have a hard time of learning evaluation functions. And so I've done some theoretical and practical analysis of this algorithm in the multi-agent framework. In terms of deployed software, I have a software architecture. Move this a little bit closer, sorry. I have software architecture called HOG, which is an open source framework that's used by researchers for doing search-based algorithms, and some of the screenshots and things I'm showing today will be from HOG. I've also worked with BioWare on their pathfinding engine design for Dragon Age, and I'll talk a little bit about that today. I do ongoing consulting with them on how to sort of best optimize the use of the engine. I have students who are currently working on moving target search, sort of a cops and robbers problem. We have a number of students who are working together on projects for general game playing, which is basically, there's a logic-based description of a game. It's handed to you, and you have to learn how to play the game as quickly as you can and compete against other people. Some interesting projects on card games, including a simplified version of Bridge and a German card game called Skat I've been working on with a professor there recently. So those are just some of the projects, some of the contributions that I've done. Today we're going to talk about single-agent search, and when I say single-agent search, the problem definition that we're usually looking at is this. I'm going to give you a start state that you're going to start in. I'm going to give you a goal state, and that may be a specific state or it may be implicit. That is, I'm going to give you a test for that. I'm going to give you a successor function, a way to get from your current state to the next state. And oftentimes I'm going to give you a heuristic estimate. That is some estimate of the cost from the current state to get to the goal. And the goal is to find an optimal path from the start to the goal. Now, in AI, we've really focused on, one of the things we focused on is building and using heuristics. We've generally focused on admissible heuristics. These are heuristics which are a lower bound of the cost to get from the start to the goal. And we've often also really focused on consistent heuristics. Consistent heuristics is basically a property that when I apply an action, if my action has cost 1, then across those states, my heuristic doesn't change by more than 1 as well. And there's a lot of actually recent work that's been done on inconsistent heuristics, where early analysis basically gave a very pessimistic view, and that's been changing more recently. And basically, heuristics are used by tons and tons of algorithms. The most sort of common are A star and IDA star. I just picked up the first couple of algorithms I could think of here. Basically, a lot of algorithms in basically just about any algorithm in AI that is a search algorithm is using a heuristic estimate. And so really the big idea is if we can improve our heuristic estimates, my search is going to be faster. My search is going to be better. Maybe I can get, if I'm looking at suboptimal problems, I may be able to get sort of more optimal solutions. So this is the big idea, but then there's sort of caveats behind that, which is, well, this may not entirely be true. So inconsistent heuristics are one example where a better heuristic may not actually speed my search. It's the case that if I have multiple heuristics, if sometimes having multiple small heuristics is better than having one large heuristic. And so but there I might be better actually not having a more accurate, larger heuristic because of the nature of the way the search proceeds. But if I have too many heuristics that are available to me, the cost of sort of looking at many, many heuristics to get a good estimate sort of is out. Although I may expand fewer nodes in my search, the actual time that it takes to perform the search may increase if I'm using too many heuristics. And so what I want to do basically is give you an overview of the work that's gone on in building heuristics. I'm not going to talk about the really early work, but sort of what's been state of the art over the last 10 years. And then we'll use that to sort of spring into what I'm going to talk about today, the new ideas. So pattern databases are sort of state-of-the-art technique for building memory-based heuristics. The idea is that we're going to pre-compute a heuristic and we're going to store it in memory. So for the sliding tile puzzle here, which I've shown, this is a permutation puzzle, and the idea is that we have a number of constants, and here I've just happened to number them. The blank is not labeled. I've numbered them 1 to 15, and any of the actions that I apply in this state space is a swapping of my constants. And so it's in that way I'm just creating permutations of the original problem. And so what we do is we want to pre-compute a heuristic for this, and the idea is that we're going to build an abstract state space. And so what I'm going to do is I'm going to mark some tiles here. In this case, the red tiles are the ones that I care about, and the ones that are white are ones that I don't care about. And I'm just actually going to erase those and say, I don't care what values those have. When I do this, it creates a smaller state space. Because now I can't tell, whatever the numbers that were there before, I could swap them around, and the abstract state space looks the same. And so the idea is that now I can create a smaller state space, and the state spaces actually can be exponentially smaller than the original state space. We'll do analysis in a couple minutes. And so actually now we're able to solve an entire problem like this and fit the entire solution of the problem in memory, where I wasn't able to do that before. And now if I come to any state in the world and I need to know a heuristic estimate, I simply apply this abstraction, erase the tiles that I don't care about, essentially. And then I go look up and say, well, in that problem space, what is the exact distance to get all of these tiles to the goal? And that gives me a heuristic. So if you want to analyze what's going on with this approach, we say, well, the branching factor is some constant b. And we assume that we're going to search to some depth d. So the size of my state space is then b to the d. And what I want to do is basically analyze and say, why is it that pattern databases work? And so we can do some fairly simple analysis. We're going to assume that we can store some fraction of the entire state space, so a fraction 1 over f. We're going to assume that in the abstract state space that the branching factor is the same as in the original state space. And I basically want to say, what is the maximum heuristic value that I can get from my state space? So it's a fairly simple equation. The amount of, basically the amount of memory I'm going to have is some fraction of the original memory. And now I'm basically going to be able to keep some exponentially growing smaller state space until it matches the size of this fractionally smaller fraction of the original state space. And so we simply just solve this equation. We get this function here, or this value here. And what it says is the distances which I'm going to get in my new state space, which is c, is going to differ from the maximum or actual distance in the original state space only by, I'm going to subtract off the log of the fraction that I'm reducing the size of the state space by. What that says is if I'm only subtracting a small value, that it could be much worse. If I had to divide by a value, then I'd be getting a much less accurate heuristic. But if I can keep most of the state space in memory, and the more state space I can keep in memory, basically I'm going to get very accurate estimates of distances from an abstract state space. So to make that concrete, in the 15 puzzle, which I just showed you, if I build a 60 megabyte pattern database, so this is the pattern database with 7 tiles in it, the maximum heuristic value I get here is 54. Now the entire state space is 10 terabytes. And so of course we can't keep that in memory. But the maximum width of the actual problem is 80. And so here I have about 1 million times, not quite 1 million times reduction in the size of my state space. And we think about, well, what is the log of 1 million is roughly 20. Then the distance here, I've sort of lost 20. I've actually lost 26 from the perfect heuristic. You see that this correlates fairly well. This is a fairly reasonable predictor about what happens to my heuristic estimates. And so, of course, we can fit more than 60 megabytes in memory. And as we can build large heuristics, because of this exponential growing state space, I can get good heuristic estimates. Yeah. Right.
But really what you do care is that some of the numbers have already I've defined a smaller state space. You have defined a smaller state space. What you really care about is that some of the things have already been pre-ordered, right? So 1, 2, 3 may already be in an order. And you can't just totally ignore it, right? So your state space actually grows.
So my actual state space is actually just these numbers here. So these are blank tiles, have no values on them. And the ordering of those...
No, but if you go one back, you will see that they do have a value. They have a value.
Have a value.
One should probably stay where it is, right?
Yep.
2, you really want it to move somewhere else.
Mm-hmm.
So once you've done some partial ordering,
Mm-hmm.
your state space really has to include that ordering that's already in place, doesn't it?
So in these heuristics, actually, I don't have that information at all in the heuristic. But this is an example where if I had 2 heuristics, I could have one that included these tiles and another one that included these tiles. Then when I took the max of those 2 heuristics, then both of those, it would combine, one heuristic would combine some information from some tiles, and the other one would contain, so this heuristic on its own actually is a pretty poor heuristic because I only have, I'm not considering all the information about all the tiles. So there's a number of techniques that are used to add the information together, and there's a general theory about how that can be done. Does that answer your question? Yeah. Okay. Okay, yeah, so I mean, there's a whole body of work on how to do pattern databases. What I just want to show here is basically this analysis that says, why do they work on exponential domains? And the reason why is because the error we get is simply this log based on the amount of reduction of memory. And so, again, 1 million times reduction in memory, and I mean, relatively small reduction in the size of my maximum heuristic value. This is less than a factor of 2. It's about a 1/3 reduction. So let's look at maps. If I was going to do pathfinding, and in something like a map, how would I do abstraction and what happens in this case? So what we're going to do is we're going to take a map and we're going to build a graph. Because it's easier to talk about a graph than a map that represents sort of the low-level states in my world. And what I'm going to do is I'm going to build an abstraction by finding groups of states that are similar, close by to each other. For instance, I could find small cliques. Now this is an easy problem in a map because the largest clique I can have is a 4-clique. So I could find something like that and group those together. And basically, I would take a group of states and say, this group of states in my abstract map is going to become one state. So we can see example here. This is my original state space. And the grid here, the points on the grid are states in the original state space. And then we've applied one level where we actually took cliques and turned them into single states here. So this state actually represents 4 underlying states. And we end up with something that looks like this. And so here we go from 11,000 states in the original map to about 3,500 states in the abstract map. You can see this maintains the structure of the problem when I apply this. And you can do this multiple times. So if we try and do the same analysis of what's going to happen if I try and build an abstract, so before we basically solve problems in the abstract state space to get a heuristic, we would do the same. We could try and do the same thing here, whereas I basically compute a solution from a particular state here and see what are the distances that I get. So a 2-dimensional map grows with the radius of the search. It basically grows r squared. And so if I want to know then what is the same constant here, sort of what is the maximum heuristic value I'm going to get, we can do the same assumptions and solve the same equation. What we see is we actually have a dividing factor here. We divide by the square root of this fraction. So what that says, if I abstract the state space by a factor of 4, even a factor of 4, I get a factor of 2 reduction in the maximum heuristic value that I'm going to get, which is quickly going to be a very inaccurate heuristic. And so in these mazes, these maps here actually, this isn't the entire map. Actually, this is just a portion of the map. The width of this state space is approximately 157 157 actions to get across the state space. And when I apply the abstraction, it's divided by a factor of 2. So again, the theory here is actually fairly close to predicting exactly what's going on. But if I'm trying to build a heuristic then, for a state space like this and trying to do it in the pattern database way, it's not going to work because my heuristic estimates are going to be very inaccurate. You could try and think of sort of trying to fix this by multiplying or something like that. But in general, that won't give you an admissible heuristic. If you're interested, you can talk to me about those ideas later. So of course, the obvious thing from graph theory is what should I do if I need a heuristic? And in fact, I need a heuristic between any 2 states, because in something like a map, I don't have a single goal state. Well, I should just run all pairs shortest path, right? Now, if we assume that there's n states in the state space, I'm going to use n through the rest of the talk as the number of states in the state space. We know that takes n squared memory, and it takes n cubed time in theory to run. Now, because our branching factor is limited and we only have sort of local edges in our graph, it would actually take less than n cubed time to run. N cubed time would actually be prohibitive for commercial maps. But if we commonly have a million states, so that'd be like a 1024 by 1024 map, storing the all pair shortest path data would take 1 terabyte of data. No commercial game, we don't have media that's going to ship with 1 terabyte. And of course, I have many, many maps in a game. So this isn't a feasible approach. So I just want to talk a little bit about games here and sort of what's going on. In games, actually, we're never usually looking for optimal search algorithms. We don't need the optimal path. Most humans can't tell the difference between an optimal path or a slightly suboptimal path. And optimal in terms of distance isn't necessarily the optimality metric that a game company is looking for. They sort of want realistic-looking paths, smooth-looking paths, and other things like that. But generally, we're willing to trade off speed for optimality. But as I said previously, basically, we're still going to use heuristics in a search like this. I may weight the search to try and speed up the search. I may use an abstract state space and do search in an abstract state space. There's a way I can do search and refinement there in a way that doesn't require that I'm getting a heuristic for it, but I'm actually still able to generate paths. So let me just show you a little bit about what actually is going on inside Dragon Age, which is coming up by BioWare. The game was supposed to be released a year ago. It was supposed to be released now, and now it's been delayed about another 6 months. They're trying to get the console and PC version to come out really close to the same time. So I'm looking forward to this game finally being released. But in 2006, BioWare came to us and basically said their pathfinding approach was really bad. It was taking up to 100 milliseconds to plan a path. And ideally, they sort of have 1 to 3 milliseconds to do pathfinding per frame. But they'd really like something faster than that because you've got 20, 30, 50 creatures in the world that all need to do pathfinding. So you'd really like something that takes 100 microseconds or something like that. So they basically came and said, well, what do you have in terms of your technology? Here's our design constraints. And I took basically our pathfinding technology that I had worked on and came up with a custom design that would meet their design constraints. They came back and said, that's great. We love it. We want to use it. And then they came back and said, we don't have anyone who can implement this quickly. Why don't you come and do it? So I went into BioWare and basically worked on their game engine for them. And the idea is, like we look at abstraction, we do build an abstract version of the map. There's some parameters that basically try and reduce the memory on that. And we find a path in the abstraction, but instead of using that as a heuristic, there's a refinement process that turns an abstract path into a real path. Something nice about that is refinement can be done incrementally, and so we can actually start moving before refinement finishes. So Dragon Age is also known as Dragon Age Origins. Hopefully you can see these. This is from the beginning of one of the origin stories. This is the map. This is a screenshot from the original implementation. Under here is the map. At this point, we weren't allowed to show any IP or any content of the game. So all you can really see here is the layout of the map. But this is the human noble origin story. And so this is basically shows, and this is built automatically, the high-level view of what the map looks like. And then this is refined. I apologize. I'm pointing over here to people on this side of the room. But this is we can use this to refine into paths. And sort of the success, one of the nice successes early in this implementation was that at one point they hadn't actually exported pathfinding points across a door right here. And so I was had my character standing on one side of the door, and I just clicked on the other side, which is just about 2 meters away, and said walk there. But the pathfinding didn't know that you could actually walk across the door. And so it turned around, it ran through the room, opened the door, went out, went down a hallway, went down another corridor, and came up another flight of stairs. and ended up 1 meter away from where I had clicked to begin with. Now, in that case, of course, there was a shorter path, but at least proved that the engine was capable of doing some really complicated pathfinding. And frankly, in previous Bioware games, it's been very annoying where I can see I want to go there, but there's a big, long path to get there, and I don't really want to have to navigate back one step at a time, like after I've gone through a whole dungeon. So this feature will be in their engine now, that if you can see somewhere, you can click on it. Sometimes it's a little bit hard to get to actually click on the pathfinding points, but it should work in the game. Yes?
On or not. So in the code that actually ships with the game, do you use an admissible heuristic or not?
Yeah, we have an admissible heuristic there.
And did you entertain lifting that?
So actually, in the abstract search now, we use a weighted. So there's some complications here. We use a weighted heuristic here, and actually, in the abstract search, the heuristic ends up not being admissible. Although it's admissible for this graph, it's not admissible for the underlying search. And then the heuristic is weighted for the abstract search. So in that case, it's inadmissible as well. But then when we get an abstract path here, we do another search in the actual level of the map. And that is done with an admissible heuristic. So at that level, we do. There's some optimizations. There's creatures. We have creature costs and trap costs. And there's a lot of things on top of that to actually make it work. So does that answer your question? Yes. Yeah. OK. So let me just show a video here. This is the sample map that we came up with. What you'll see here is basically we're going to zoom out. You'll see it's sort of a complicated path to find. The path is planned, and you'll see as our PC here starts moving, there's a bug this day that made the guy not appear, but it's actually good because otherwise it would have basically we weren't allowed to show what the creature looked like at the time I made this video. So this daily bug worked on our behalf. So we'll zoom out. We'll see the path being planned. The path is then smoothed as we walk along it, and the path is actually still being planned as we start walking. So you can see all of that in this video. There we go. OK. So we're going to try and walk to a place over here. As soon as I click here, we start planning. So we're still planning. We're still planning. We're done planning. We do smoothing. If you watch along here, this is where the smoothing is going to take place. Smoothing is sort of happening incrementally as we walk along the path. So this has been smoothed now. This hasn't been smoothed yet. As I walk around the corner here, then we see smoothing is occurring on this part of the map. So this is single agent pathfinding. There's a lot of issues that are still sort of being dealt with in terms of multiple agents, multiple creatures, and how that's dealt with. We don't sort of have the full research solution into the game, but they're happy with this right now. They assured me when I left that they could handle all those issues. Now I'm talking to them about how to sort of cover up some of the defects and what's going on. So in 2008, though, actually they gave me a call, and I sort of checked with them regularly because I gave them this code, but there's no guarantee, what they're going to do with the code after I leave. And so 2008, they contacted me and said, can you come in and maybe work on just cleaning up some things with the code and helping us with the way that the engine is working now. And this is good because there were a number of bugs that hadn't been introduced and things that they didn't always understand. When I looked at the game, I sort of see two large-scale issues. One is on the really large maps, we couldn't solve the largest problems on slow machines. And this is something that sort of is my personal goal, is to be able to go on any map, be able to click anywhere that I can see and walk there. And there's also some odd behavior on some maps because of the abstraction. I'm going to show what this is in a minute. But let me just say what some of the possible solutions were. One is to try and increase abstraction granularity. Another one is to try and build another layer of abstraction. And the third would be to try and improve heuristics. And this is actually why I'm talking about this here, is because one of the things I looked at was trying to improve the heuristics, but there's no literature to draw on. There's sort of no good published ideas in AI. And it's possible that people have done some of these ideas. They end up not being very complicated in other domains. I know other people have experimented with them, but in terms of actually studying them, we weren't able to find any published work. So basically, though, I didn't have a good understanding of how we could use heuristics, and so we did these first two approaches. Now that I have this research, I sort of know how we could have built better heuristics for them. So this is the same map I showed you before, and what I'm going to show you now is what it looks like with another level of abstraction on top. So this is the same map again. What we've done is what was red before sort of become a high-level yellow version of the map. it's sort of hard to see. And then underlying that is a red level of abstraction. And this is a finer granularity of an abstraction. Now, the reason we need this is actually a map like this. This is from one of the other origin stories in the game. And if you look at this map, it's actually a straight line. It's just been wrapped around in a circle. So you can basically only walk one way on the map, but you have to do it in the circular manner. And so what it means is that actually you can stand right here, and you can look over this wall, and you can click on that part of the world. And if I begin to search, my initial search is in my abstraction, I'm basically going to have to expand all the nodes in the entire graph, because my heuristic basically doesn't know that I need to be going this way versus trying to search this way, because it thinks, well, there's got to be some passageway this way to get across that wall, where in reality there isn't. So this is the case where I needed this level of abstraction to be able to expand all the nodes in the abstract map and to be able to find the path. But what we're going to do is actually, if we look at this right here, what you see is most of the time we sort of see these X's. This basically means it's a very free and open area. If we look at the yellow part up here, what we see is there actually aren't X's in between here. What that means is there's some obstacles here. So let's zoom in on this part of the map and see what's here. What we see is that it's sort of hard to see here, but there's some bunk beds here. And what this is saying is basically the abstraction has figured out that you can go around the bunk beds, but there's a very narrow passageway in between. And it's actually like one square off from figuring out that you could walk through here. If you look at the underlying data, it just barely missed sort of figuring out that we could walk through here. And so what happens is if you're standing here and you say, I want to walk here, sometimes you'll figure out that you can walk right in between these bunk beds, and sometimes you won't, and you'll walk around one of these other ways. So it creates sort of strange behavior. And this is where, if I create this red level of abstraction, it represents the underlying geography and the underlying obstacles and things like that much more accurately. And so in that case, it doesn't, I don't have that problem. I see that I can walk between the bunk beds or around them. So this is an example where the low level gives us some information that the high level doesn't give us. But we need the high level to be able to plan fast enough to sort of do these long, difficult searches. This is something where a heuristic would help us, but we didn't have one. So this is one of the largest maps in the games. This is a place called Ostagar. If you go to Dragon Age's website, you'll see a lot of videos in Ostagar. And so this is actually, you can see, is a very large map. These are, the red level is a 256, there's 256 cell points inside a red, for every red point, and then it's 4 times that size for each of the yellow points. So I'm just going to show you an example here that shows we can now actually, I'm going to start from standing here. I actually can show this. There we go. So the player character right now is standing here. We're going to ask him to walk over to right here, and we can watch that happen. If it started. There we go. So it's planning. It's actually smoothing the path as you walk. It's gradually, incrementally able to find the path to here, and at the same time, it's walking along the path. So this is the engine. This is how it should work in the large game. Hopefully, if you're standing right here, the one place you can do is you stand right here. You can look down and see here, and you can click there. And that's you can't actually do this in the game because you're not allowed to zoom the camera out. But in the real game, there's similar paths that you can do. OK, so for Dragon Age, another level of abstraction fixed most of the issues. But we had this outstanding question of how to improve the heuristics. We know that we can't use pattern databases, and I need sort of a heuristic between any 2 states in the world. So we're going to start out with this idea that sort of looks like abstraction. What we're going to do is we're going to say randomly choose k points in my state space. I'm going to label these canonical states. And then I'm going to find the regions around these states that are sort of the closest points to each of my states, and I'm going to call those canonical regions. So let's just look. This is a simple map. This is just generated rooms. There's random rooms with doors in between them. Sort of make for interesting maps where we can scale them well. If we do this here, we can apply an abstraction. Each of these red points is a canonical state, and then the colored regions are the areas that are closest to each of the canonical states. I didn't use a graph coloring algorithm here, so some of my colors are actually the same in adjacent regions, but this gives you an idea. So what I want to do is talk about what can we do if we have this sort of representation of the world. But let's look at it sort of in a more abstract view. So what we have here is we have a set of canonical states, and we have regions around them. And what I'm going to do, actually, is I'm going to store, for all canonical states, I'm going to store the distance between all pairs of canonical states. So this looks like something like all pairs shortest path, except it's sort of like a limited pairs shortest path problem. And the difference between what's been done before and what's being done here is instead of storing the distances in terms of the abstract distances in the abstract state space, we're going to store the actual distances in the real state space. So because these are actual states in the world as opposed to abstract states, which are a group of states, I can compute an actual distance here. The next thing we're going to do is for every state in the world, I'm going to compute the distance from every state to its closest canonical state. Okay? So the memory cost of this is sort of k squared because of all pairs shortest path. And then for each state in the world, I actually have to do two things. I have to identify which is the closest canonical state, and then I have to identify what is the distance to that. Sometimes that can be done implicitly. We're going to store it explicitly for right now. So I'll do that similarly for another state here. And then if I want to build a heuristic, what I'm simply going to say is, well, if I know that this is an exact distance, and I know these are exact distances, then I can take that exact distance, I can subtract the distance from the canonical state, and I can turn that into a heuristic between the two states. Okay. If we can use something like the triangle inequality, will basically give us a guarantee that this is an admissible estimate. Okay. So the key here is that we're using states from something that looks like an abstract state space, but we're not using abstract distances. O of k squared memory for keeping the canonical states and the distances, and then the secondary data is sort of O of n to keep, it's 2n exactly, because I need to keep which is the closest canonical state and what is my distance to it. So again, we can write the heuristic here. If I have the closest canonical state, I'm subtracting two parts here. And so what it says in terms of canonical states, if I want to choose where to put them, I want them sort of as evenly around the state space so I can minimize these distances in the world. Now, there's a problem here, because if I have an example that looks like this, in this case, I have this distance here, and I'm going to subtract it off, but it's going to be just about perfect, because the distance between here, well, A is sort of like right along this path, and so my error will be minimal, but I'll get the exact same heuristic estimate with a situation that looks like this, because I can't tell this distance which direction I'm actually having to go that distance. And so there's an idea that we can use on top of this here, which is I can sort of look out at the broader picture. And in the broader picture, I have other canonical states and other canonical regions around. And in fact, since I have the all pairs shortest path data, I do know the exact distance between these canonical states. So what I can do is if I have the distance between this state not only to the closest canonical state, but to some other canonical state as well, then I can use that distance. And the more basically other canonical states that I can store the distance to, then I can improve my estimates here. Because now when I subtract, I'm actually going to get a very accurate heuristic. Okay? So the idea here is that instead of only storing the distance to the closest state, we're going to maintain the distance to some number of d canonical states. And now what this means is I have actually many, many heuristic lookups that I can do. So to sort of, for all I and j, I can take the max over the choice of various canonical states for each one. Yes?
Yeah, are the D states the nearest canonical states to it, or just arbitrary?
So what we've done in practice here is we've chosen the D closest canonical states. Yeah. Good question, though. Now, something we can notice here, of course, is that what if two states share the same canonical state? Especially as I have more and more canonical states, then what my heuristic is going to look like, well, this distance will be 0. And then I have two terms here, which are just subtracting, which is going to give me a heuristic which is less than 0. This doesn't make any sense. And this leads to an observation. Of course, it's just a simple application of the triangle inequality, that if I have two distances here to a single canonical state, I can combine them together into a single heuristic estimate. The heuristic estimate is simply the absolute value of the distances between these two states. Now, there's actually two things that we can do with this. One is when we're applying the canonical, what we call the canonical heuristic, using the canonical states, we can basically, when I happen to have two of the same canonical states, I can just apply this rule. But I could also do something where I simply only build differential heuristics and just try using this rule. And we'll show actually that these two ideas end up being one and the same in 2 slides. So as I said, we're using the triangle inequality here. The placement scheme now, if I'm trying to do, so we're just going to look at if I only have a differential heuristic, my placement scheme is going to be much different. Because now what I want to do, instead of sort of having them uniformly across the state space, when I'm subtracting these two values, I want to sort of get them as far away. There's a deeper explanation, but I want to get them as far away from other states so that my distances will be as large as possible. So when I subtract them, I'm most likely to get large values. And so this is an example. We have a placement algorithm that does this and shows actually there's significant improvement from using this. These are the placement of canonical states for a differential heuristic. This is a map from old Baldur's Gate, is an old Neverwinter, or old Bioware game. The idea is you want to sort of put them far apart from each other, and that way we're going to get sort of long distances. So when I choose any two arbitrary states, it's sort of likely that I'm going to get nice long distances. And so this is a differential heuristic. So if I look in general, what I said is that we have k canonical heuristics. We're going to take k squared memory to say the shortest path between all canonical states. And then is 2 times d times n memory for storing what is the sort of d closest canonical states and what is my distance to those states. Now, if I happen to be the case that d is equal to k, so I have the distance to all canonical states, then I don't need to say which canonical states because I have the distance to all of them. So that gives me a factor of 2 savings. If I don't want to worry, if I'm storing the distance to every single one, then I just order them. And so what we look here is, this is an example of just fixing the memory. I say I'm going to use 10 times n, where n is the size of the map. If I'm going to fix my memory there, what different heuristics can I build? So what you see is the d, I have a 2n cost on d. So this would be 2n. And since the cost for k is k squared, then I have sort of the square root of 8n. Canonical states would give me, that's the number of canonical states I can have if I have d equals 1. So as I increase d, then I have fewer canonical states, but I can keep more distances. At the point where d equals 5, in theory, I should have k equals 0. But in fact, there, I have my canonical states. I actually already have all the distances between them. So here, if I were just to naively apply this, I would have 5 canonical states. But as I said, we can double the amount of memory we use because I don't have to identify which state. I just know my first entry is the first state, my second entry is the second state, and so on. So we're going to look at results in 2 domains. I'm going to look at pathfinding, and that's an area of interest to me. But I'm also look at another problem, and I have results on like sliding tile puzzle that illustrate some of these, some of the other insights that we have, but I'm not going to show them here today. So the articulated robotic arm is an interesting problem where I have a robotic arm that can move, and basically this is an example of a problem where I have an implicit goal state, but I'll describe it in a moment. So what we experimented with is we built a number of 512 by 512 maps. We experimented with a number of different types of maps. So the results I'm showing here are ones that are composed of rooms with random doors opened in between. The lengths of the paths that we're experimenting with are sort of evenly distributed in buckets between length 256 and length 512. We looked at 5 different maps. The variation over maps isn't large because these are randomly created maps. And so we averaged over 3,200 total problems. And I'm going to use A* to search here, so no weighted search or anything like that. My default heuristic is an octile heuristic, which is basically an 8-connected heuristic. So it knows either go straight or I'm going to take a diagonal. And that's how I compute the actual distance. The first thing I want to look at is a comparison to all pair shortest path. So if we look at all pair shortest path, what this is the number of states that I have. This is with a differential heuristic. The reason I did this with a differential heuristic is because differential heuristics can be built incrementally. I can easily just add one more differential heuristic in the world. And so it's very easy to run this experiment, where it's very, very expensive, or a lot more expensive to build a canonical heuristic. And what we see here, so we run experiments actually up to 125 canonical heuristics, and I just interpolated for the results beyond that for running if you had the full all pair shortest path data. So notice first, this is a logarithmic curve here. So the amount of, the number of canonical states is quite large here. This is for a smaller map than the previous experiments. My heuristic value with octile, so this is actually, the first point here is my octile heuristic. It's no memory-based heuristic at all. Since you can't plot 0 on a log plot, I had to plot it at 2 or something like that. And what we see is actually very, very quickly here, we get close to the optimal heuristic value. And we're only off by like less than 1 in terms of our heuristic value with 125 canonical states. In terms of the number of nodes expanded, I'm also dropping very, very quickly. There's only a factor of 2 reduction that's possible with going with more than 125 canonical states. Of course, at this point, if I have the full all pair shortest path data at every point, I just have to do sort of a one-step look ahead. So that's sort of really, really fast compared to here where we are generating the entire path. Now, this is a log-log curve. Both of these are actually log-log. And so something that's sometimes deceiving, on a log-log curve, a straight line looks something like a bowed-out curve. And so this, on a log-log, is a bowed-down curve. And actually, if I didn't have it on a log-log plot, it would look like it dropped straight down and then went straight across. Because we're basically using a very, very small fraction of the full all-pair shortest path data. What this says is all-pair shortest path, which I've seen research papers where people say, well, we can't do all-pair shortest path, and there's nothing else to do in terms of heuristics, so we're going to do this other idea. Well, this sort of shows that basically all-pair shortest path is massive overkill in terms of what I need to get a good heuristic. I only need a small fraction of that data to get good heuristics and to be able to minimize my amount of work. Now, these are experimental results. Here we fix the amount of memory at 10 times the size of the map. And so what we see here, k is the number of canonical states. As I increase the distances here, the number of canonical states decreases. On these particular maps, on average, we expand 21,000 nodes using our baseline heuristic. We have an average heuristic value of 309, and it takes about 300 milliseconds to plan a path. These are average values. So as I begin to add my heuristic here, basically we see nice improvements. This is the multiplicative factor over octile, and this is the multiplicative factor in time. So it does cost something to look up my heuristic in memory, which is why these values aren't exactly identical. What we see actually is this nice little bowed curve here, is that the best case, at least for the canonical heuristic, is to use the d of 3. And so what see the number of states here is minimum, and the time here is minimum. And basically what's happening is the number of canonical states decreases, then I become farther and farther away from my canonical states, so my heuristic becomes less accurate. But as I increase d, then I basically am able to do a better job of increasing my heuristics because I can use more canonical states to localize my location between. What we see with the differential heuristic here is that just using 5, which is sort of the naive implementation, we don't do very well. Actually, only a small factor of improvement. But when I go to 10, we actually see a large improvement. So this is a 6 times improvement in nodes expanded, a 5.5 times improvement in speed. There's something really interesting going on here. So this is better than my canonical heuristic. But if you look at my average heuristic value, this is for the average heuristic value for the start state in my problem. I have a worse heuristic value for my differential heuristic than I have for my canonical heuristic. In fact, for all of these are higher than 370, which I have here. Yet the number of nodes I expand is much less here. So this is an example of what I was talking about earlier when I was saying that better heuristics or better heuristic values don't always result in less search. And this is actually what's going on. So this is a histogram of the values of the heuristic values that I encounter during the search. This is over basically the same data here, and then I've graphed it for both problems. And then this is the number of nodes with each particular heuristic value. And what you see here is for states that are a long way away from the start, we have very good heuristic values, both for the canonical and differential heuristics. But as we get closer and closer to the goal, it ends up that we actually do much worse with the canonical heuristics. Basically, there's two things that are going on here. One is that sort of at the large distances from my canonical states, I'm having to subtract a large value off my heuristic. And that value is sort of insignificant when I'm a long ways away from the goal. But when I get close to the goal, subtracting that value causes a significant increase in the amount of work that I have to do. And so we don't have that exactly the same factor with a differential heuristic. The other thing is that my canonical heuristic is an inconsistent heuristic. And so there's some things about node reopenings and other things that have to do with being an inconsistent heuristic. That is, my heuristic values can jump when I move from one canonical state to the next. So the next problem we're going to look at is the actuated robotic arm. So this is the configuration in the arm. The red part here are obstacles in the world. The white part here is the arm. And what I'm going to just show you here is this is the search space. These are actually the nodes that are the states that are being expanded as I try and find a path to get the tip of the arm right here. So the idea is that you just say, this is where I want you to get the tip of the arm, and it has to try and search and find a way to get the arm there. Now, found it, it shows the path, and then it'll repeat. Most heuristics in this domain are really poor because what we have is we have a distance from the current tip of the arm to where I want the tip of the arm to be. And those distances don't correspond well to actually actions in the state space, which is moving the arm 1 degree in any particular direction. So there's two ideas here that we used. In fact, most work on this in the literature is on finding suboptimal solutions because optimal solutions are fairly difficult to find. So one idea is using that we have is basically instead of searching from the start state to all possible goal states, we actually generate all possible goal states and search backwards towards the start state. And what that does is now I'm always searching from an arm configuration to an arm configuration. And so that actually really improves my baseline heuristic estimate. The other thing then is we added differential heuristics. The size of the state space is 132 million states. So what we're going to look at here is this is sort of the baseline, the previous approach. We had a set of 400 problems of which we solved 100 of them. Or we solved all 400, but 300 of them using this reverse search where it took less than a second. And so we're looking at the hardest 100 problems here. Now, those other 300 problems are really, really hard for the previous baseline search approach. And so that approach actually took 40 hours to solve the problem set, where it takes less than an hour to solve, even with this reverse approach. So what we see here is, and also the heuristic that we're using in the original approach is to actually run A* to compute the distance of an optimal path. And so that A* computation of the heuristic is a little bit expensive. So what we see here is we have a factor of 2 reduction by turning into a reverse search in the number of nodes, but we have a factor of 8, almost 9 times reduction in the amount of time, because now I have a very fast, very accurate heuristic. And as we add differential heuristics here now, we see actually very impressive improvements. In terms of speed, we're up to 100 times faster on this problem set. And if we look at the entire problem set, we're actually 500 times faster than using the baseline of just the distance from going from one tip state to another tip state. Now, some comments. If we look at pathfinding, I don't have 10n memory to store sort of in my high-level map. Maps are large, and so map basically fills memory. So I don't have a memory to do that. But what I do have memory to do is I have memory to use an abstraction like this, a heuristic like this, in my abstract state space. So what this would allow me to do is build a higher resolution abstract state space where I can afford something like 10n memory to build my heuristic on top. And then I don't have to build the second layer of abstraction on top. So I didn't understand this when I was at BioWare earlier in the year. This is work that came out of that. And this sort of answers the question of what is the other thing we could have done for BioWare to help them with that particular problem. So if we look in general, there's a lot of previous work. Basically, 10 years of previous work has been done on heuristic that's oriented towards problems that grow exponentially. And this is sort of the first new work that's been done towards domains, in this case, domains that fit in memory, but also just towards what happens if my problem state space doesn't grow exponentially. There's problems in genetics that actually, like sequence alignment, also look like that. And we have significant improvements in these domains. There's a lot of interesting research to be done here. One question is, how can we reduce memory overhead? Can we compress these? There's some very easy ways where we could compress the amount of memory used even further. There's questions of what does it mean to optimally place states? How should I choose my states? The canonical heuristics, there's actually a lot of information stored there that we're not using in the canonical heuristic. And so I have a feeling that there's a number of techniques we could use which would improve our ability to use the data that's out there to be used. And so we may see in the future that we can use canonical heuristics in particular ways where we improve the performance. And part of this has to do with inconsistency. And of course, there's work in trying to apply this to other domains as well. This is work that actually there's a master's student who was asking questions about these ideas and helped sort of push along this work initially, that he was sort of just asking what would happen if we tried some of these ideas. Ariel Fellner is one of the people who's done a lot of work on pattern databases. And so he was also pushing me and saying, I really want to know how can we apply the idea of pattern databases into other domains. And so he is co-authored a paper that we have submitted to HCI on this. Jonathan Schaefer also helped us in sort of refining the ideas. And Neil Birch is a programmer research assistant who did our initial robotic arm implementation and gave us a lot of insights on what was the wrong thing to do so we could then do the right thing after that. So thank you. Any questions?
For the canonical The choice of canonical states is random, globally random?
So what we actually are doing is I'm actually building a abstraction like I would normally build an abstraction, because those tend to place my states fairly uniformly throughout the world. In the paper that we've submitted, we compared the random and the sort of the smarter placement that does a better job of putting them evenly in the world. So both approaches can be used, and random isn't that much worse than it is worse, but not significantly so.
Yeah, I have a second question. When you have multiple levels of granularity, so you have an abstract layer, is that global? In other words, you have both levels of granularity for the entire state space? Or
Yes, it is. That's global through the entire state space. So when I do planning, I do a plan on the entire abstract state space at the highest level. And then actually, if that's a really long path, I divide it in half, and then plan the first half and plan the second half. And then I take that and I divide it into very small segments and then plan each segment one at a time.
So it seems like that there's some potential for using these same techniques, standing them on their head. So if you were, rather than solving the plan generation problem, solving the plan recognition problem, where you're given a series of actions and you're trying to infer the plan that the agent is trying to...
Yeah, so actually there's a former postdoc from the U of A. He's at Google now, Finnegan Southey. He actually used my HOG framework to do exactly that, which he was trying to do. Basically, if I observe you walking, and I know how these planning algorithms work, can I figure out where you're going and where you've been doing? So there is some work on doing that. And of course, if I have the algorithm, I can. So it was saying in a game, if I see someone walking somewhere, can I guess where they've come from?
And does the abstraction approach help, or?
Yeah, I mean, so abstraction in general, there's a lot of computations that are really hard to do on a large state space, but we can do exactly on an abstract state space. And so abstraction is generally useful for doing sort of expensive computations and getting an approximation of what I would want to do in the actual state space.
You mentioned early on that I guess memory-based heuristics were especially good for permutation problems. Is there any other sort of characterization of when they're good, or?
So if you look at basically all the domains that they've been used on is forms of permutation problems. Recently they've been picked up by the planning community. They're looking at taking like strips and something like that and being able to turn that into a pattern database. And so there's some recent work actually on different representations on binary decision diagrams and some things like that for representing them. So there is some work that's going in that direction, but it sort of hasn't hit sort of mainstream. It's sort of, I think it's very preliminary at this point.
So I'm curious, how often is your algorithm wrong? In other words, how often could you have either done better, what percentage of time, and are there cases where it just doesn't finish?
Do you mean in the implementation for Dragon Age? So I don't have like raw numbers in terms of what I have measured is I have measured like how suboptimal is it from optimal paths. Of course, optimal paths are measured on a grid, and in the real world, you're allowed to walk on straight lines. So there is a fair amount of suboptimality that comes from that. So on the grids, we saw sort of on average about 10 to 15% suboptimality. In the actual game, there's other people walking around. There's obstacles. We put weights on traps. We put weights on if someone casts a spell, then there's a weight there that says try and walk around the area where the spell has been cast. And so the real world is actually so complicated that measuring that in terms of the actual game is difficult. But some of the things that are interesting challenges for the game is if I have a tight doorway and I have a lot of people that want to walk through it, that's one area where I basically went in last week, or 2 weeks ago now, and we put something in the code that says if I'm failing because of situations like that, we turn off all the enhancements to pathfinding because of these constraints. And sort of I know how to solve that problem, but they're not interested in seeing that implemented in the game right now.
Actually, I guess related to that, when you gave the example of trying to go to the other side of the door and not knowing that you could go around it, what do you do if there's a sort of non-uniform difficulty of walking, like through water or mud, or is that any part of these games?
Yeah, so for Dragon Age, in terms of walking around, we don't have that non-uniform difficulty, except the one exception is traps. And we have traps and we have area effects. And so the one thing that we do is in the abstraction, an area effect is generally a large effect. And so in the abstraction, the state spaces in the abstraction that we use actually correspond to low-level state spaces. And so what we do is when I want to plan, in the abstraction, I actually check and say, is there an area effect on top of this location right here down in the world right now? Is there someone standing on top of exactly this location right now? And so we take some of those things into account by weighting the cost of my edges and also weighting the heuristic in those nodes. So that encourages me to go around. So one of the things that I put in earlier this year was basically, we had a couple bits of extra memory, and so I used them for some of these things. Around player characters, there's now basically a halo that says, these are places that are more expensive to walk. What was happening before is that someone would try and walk by you. You would say, go to the other side over here. And you'd see me standing right here. And the preferred path would be to walk perhaps right in front of me, as opposed to walking around the podium, or to walk right up to me and the very last second, cut to the side, and then cut back around me. And so putting in weights like that causes much smoother behavior, because now it says, well, it's a little more expensive to go around here. So either go around or don't cut quite so close to me. Give me some personal space. And so things like that there's tweaks like that, that are sort of needed to get realistic behavior. Something else that we saw, actually was a really funny example, is there's a room, and the room had pillars down it. And the pillars were lined up exactly with the size of the abstraction. And so it ended up that you clicked on the other side of the room, and the way things worked is you weaved back and forth between the pillars. So you'd walk to the left of the first one, to the right of the next one, to the left of the next one. And it was just sort of everything sort of worked together perfectly wrong to cause that to happen. And so there's things on top of that have to do with trimming paths, have to do with preferences for walking in a straight line versus turning, that fix things like that. So there's a number of things like that given that I understand what the pathfinding engine is doing, I was able to then go in and say, well, these things are happening. If we apply these changes here, they'll fix this behavior. But they're not generally considered part of the normal pathfinding algorithm. This isn't sort of the science. This is the art of the field.
So related to that question, you've talked about interesting ways that the real-world problems from the pathfinding in the levels have affected the optimality and other aspects of the search. And as you sort of alluded to at the beginning, the designer's perspective of a notion of optimality is not what we would normally think of.
Right.
And then in just a question or two ago, you were talking about little tweaks that could improve what a game designer would think of as the optimality of the path that's selected.
Right.
Is there can you imagine a way that that type of work would not be localized tweaks, but would be also an area of research?
So there has been some recent work on actually trying to do any angle pathfinding, which is to say, can I figure out where I can walk across free space? And so that work is by Sven Koenig and some other people at USC. So that's one area that has potential to do has some of this. One of the other things that you need is something like cooperative pathfinding, where you know where other people are standing. And I mean, some things that are like adding weights around you are actually representing what we want in the world. There's a cost to walk there. And so that's, although it's a tweak, it's also sort of incorporating that into the search. But other things like cooperative pathfinding, really they add an entire another dimension to the search. So instead of being a two-dimensional search problem, now there's an aspect of time. And that actually can be done fairly efficiently. But this is something that, in particular, BioWare is a little bit afraid to, and especially at this point in the game, it makes sense. But even initially, they were sort of reluctant. They thought they had that solved. So maybe they understand that they don't now. But so there's ways that those can be put in, but oftentimes they blow up the state space. And actually, it's very important that when we blow up the state space, this is when it's very, very important to have accurate heuristics. Because like in a two-dimensional search problem, I have a bad heuristic. Well, there's some area that it's bad in, so that's the area. That's sort of the cost. If I go into a three-dimensional search problem and I have a bad heuristic, I pay sort of the volume of the bad heuristic. And so that really, especially when I have now the ability maybe to stand still and wait, it really blows up the cost of the search. And so if I don't have very accurate heuristics, then I'm really in trouble. And so there is actually another approach to getting good heuristics on the fly, which is to reduce a dimension out of the problem. So take my three-dimensional problem, turn it into a two-dimensional problem and solve that, and then use that as a heuristic for the three-dimensional problem. So that's it's another approach that sort of dovetails with this, that these sort of could be used together.
So what about the other way around? So what about the other way around? Sometimes in planning, it actually becomes better if you can get better plans or smoother plans if you move up to a higher dimensional state space, as long as it's kind of sparse in the higher dimension.
Right.
Can you so maybe if you get good accurate heuristic estimates or improve your heuristic estimates by going up in dimension instead of down?
I don't, well, so I don't know if you're thinking of a particular example. For these sort of things, your heuristic estimate is not going to ever improve by adding another dimension. But if you somehow added information that you then could take into account in your heuristic estimate, then that would be a case where you might be able to do that. So I might be able to answer something about a specific domain, but in general.
So for example, the robotic arm, instead of considering just where the tip is, you can consider the orientation of all of the joints.
Right, so I mean.
That blows up the state space, but then you have more information that you can build a heuristic.
That actually doesn't blow up the state space at all, actually. So the state space is still the same size. But what I could do there is I could say, yeah, here's the orientation of the arms. And so now I can put more constraints on the movement. The thing about that is that it's a very complicated engineering problem to figure out those constraints. So it's much easier just to actually have a memory-based heuristic figure it out for you exactly. And so you actually could build a memory-based heuristic for the robotic arm that sort of answered the question of how far the arm can move and how quickly in any particular configuration of the arm. And so that would be another way that you could build a memory-based heuristic for something like that. But it would be solving a slightly different problem. Does that answer your question? Okay.
So a lot of recent games are having way more destructible environments and things.
Mhm.
Are there particular aspects of your search that you would change to support those, or would you use this area effect type thing for that?
So the nice thing, well, I sort of quote nice thing is for the RPG or for role-playing games, in their design, they don't have a lot of areas that are going to drastically change from one step to the next. But I have done work basically showing how these abstractions, it's fairly simple to take an abstraction and modify it as the world changes. So you can completely dynamically change the abstraction as the world changes. And if you do that, then you get exactly this, that when the abstraction changes, then it just changes the way that I plan as I discover that. So we had talked about putting that into the game, but basically the changes that occur are small enough that they basically decided it's not necessary. Ends up that this abstraction actually can be built in less than a second. And so if they'd really wanted to, you could actually just rebuild the entire abstraction from scratch if a large change was happening in the map. But in this game, at least, it's not happening. But in other types of games, like an RTS game or something like that, that'd be absolutely something that you want to take into account. Except that what you really want to do is you want to say, like if it's a building that can be destroyed, you really say that there's some cost to destroy this building. And so you could do this, but you'd have to destroy the buildings along the way. It's something similar that's done is if there's a door, there's a cost to open the door. So if there's two doors next to each other, maybe that the shortest path is to go through the closed door. But if we assign a cost to that, if the door next to it's open, then I'm willing to walk around, as opposed to, well, that door is open, but I'm going to open the door right next to it, because I'm going to save myself. So that's something where we use weighting to, and I was actually very proud they put that in the game without me, to handle cases like that. So.